You may have seen people solving Rubik's Cubes, but today I want to pose a question. How hard or how long will it take to solve a four-dimensional Rubik's Cube compared to a 3D one? To build a good estimate, let's first look at how the time it takes to solve a Rubik's Cube grows with the number of sides. Now, obviously, we can tell that it's going to get harder as we increase the number of sides. But I want you to keep some estimate of how much is going to increase in your head. Now, let's look at the concept of dimensions. In one dimension, you would need one coordinate to describe a point's position. Whereas in two dimensions, it's going to be two coordinates. Following that same line of logic, for three dimensions, it's going to be three coordinates. Generally, in n dimensions, it's going to take n coordinates. Now, the four-dimensional Rubik's Cube can't really be visualized since we're 3D creatures, so we'll be using what's called a projection. Basically, you can think of the projection as a shadow of the 4D object, just like how a 3D object casts a 2D shadow, a 4D object is going to cast a 3D shadow, which will be the projection that you see. Now let's get a bit of intuition on the possible moves that are possible in a Rubik's Cube. Left, left prime, right, right prime, up, up prime, down, down prime, front, front prime, back, back prime, and so on. Now let's take all these moves and combine them and create a graph. Now it's obviously going to be massive, so we'll only deal with the small subsection here. Now each of the blue dots that you see will be some combination moves. So one could be left, the other could be left, right, up, and so on and so forth. And then if we zoom out and look at the most complicated state, i.e. the state that's the farthest away, we'll see that the state is 21. Now that we have seen some examples, let's move forward with the problem. If the most complicated state is 21, i.e. it takes the most number of moves to reach, then it acts as the worst case scenario for what's called g of n, or God's number. Now, God's number is defined as the maximum number of moves required to solve any position, such that if you were a perfect entity, aka God, and you knew how to solve every single position optimally, what would be the most number of moves you would require for any position? That's why it's called God's number. And using God's number, you get a really good estimate of the time it takes to solve a cube. Let's say you have the God's number for any given cube. Then you can easily calculate the time required by just using the previous data. For example, if we know the time it takes to calculate 20 perfect God moves, then for God's number higher than 20, we can just scale the time required with the number of moves. To move forward with the proof, we'll introduce the concept of branching factors. So, in the following graph, what is the number of states that we reach in m moves? So, we're going to have 6 possibilities as each step, and then once we go down that step, we're going to have another 6 possibilities. So, generally, it's going to look like this. For m equals to 1, it's going to be 6. For m equals to 2, it's going to be 6 squared. For m equals to 3, it's going to be, and the total number of states is going to be b to the power of m. We've learned all the concepts required, so now let's calculate God's number, or at least a bound for it. So the key insight here is think of a puzzle cube that is n times n times n in d dimensions. So the key insight here is that as the surface area grows, the number of states of the puzzle also grows. So you could say that the surface area and the number of states are proportional to each other. Also, we know that after m moves, we can reach b to the power of m states. So really think about this. When we increase the value of m, we'll reach more and more states until eventually we will have reached every single state possible, including the worst one. So at that point, the value of m will be equal to God's number. Now take a moment to think about that. You can even go back and rewind the video and really make sure that you understand what I said. So when we reach the condition that b to the power of m is greater or equal to the total number of states, and then applying the fact that surface area and the number of states are proportional, and doing some basic algebra, we get this result. Now if we plot everything into a graph, you can see how fast everything grows. To give you a bit of context, if solving a normal Rubik's Cube takes 1 second, then solving a 4-dimensional Rubik's Cube would take 73 seconds. Now, that obviously doesn't sound like a lot, but keep in mind that none of us can solve a Rubik's Cube in 1 second. So, the answer to the question that I posed earlier, how hard is it to solve a 4-dimensional or higher dimensional Rubik's Cube, the answer is very hard. Who would have thought, right? Anyways, that's about it for this video. Thanks for watching. Like, subscribe, share with your friends. Bye bye.